So welcome back to our lecture. So in the previous summer, we talked a lot about different contributions to drag, friction drag, pressure drag, and mainly a pressure drag. We saw it's something quite complicated, and there are a bunch of phenomena playing together, counteracting each other in some cases. And one of the main phenomena, or maybe the surprising phenomena of that, is the phenomenon of the drag crisis of a cylinder or of a sphere, for instance. Let me switch back to the slide to look at this again. So this is the diagram we stopped with, and we saw here that at the Reynolds number of a few 100,000, around 300,000, this is where this drag crisis is happening. This just for your reference, a few other objects, all like 2D, quasi 2D objects. And it's also happening for a full sphere. Here we see again this full picture of all drag coefficients for a wide range of Reynolds numbers. For a sphere, the well-known result here for very low Reynolds numbers is the Stokes drag result, 24 divided by Reynolds. Here we have this range where we have a turbulent wake, but a laminar boundary layer with a more or less constant drag coefficient. And then again here, Reynolds a few 100,000, we get this transition from, excuse me, from laminar to a turbulent boundary layer, which creates a much smaller wake. And by the smaller wake, we reduce the pressure drag, and we get a much lower significant drop in the drag coefficient, which also results in a reduced drag. And this is used actually in many cases, many situations. So if we manage to bring, if we're somewhere close to this Reynolds number already, and if we manage to tip the flow a bit over the edge of this drag crisis, we can overall significantly reduce the drag of an object. This is, for instance, done in in golf balls, right? If you know, if you look at a golf ball, you see all these little dimples, and you may ask what these dimples are good for. And at least that's one theory. One theory is that these dimples are actually disturbing the laminar boundary layer, and they're tripping it to make it turbulent. So the Reynolds number of a golf ball is not quite high enough to go through the drag crisis by itself. So they added the dimples, and the little dimples make the boundary layer trip earlier at the lower Reynolds number, so you can go through the drag crisis, with the result that you have a lower drag on a golf ball, with the final result that the golf player can hit the ball much farther than without dimples. I mean, this is something that is known. You can test a golf ball with dimples and one without dimples, hit it with the same speed, and the golf ball with dimples will fly much farther. We'll come back to that in a few minutes when we look at sports ball aerodynamics, and you see there's a bunch of other interesting phenomena connected to this drag crisis. Let me just quickly close this part by looking at this diagram, just something for you to remember, because I think it's quite a fascinating result. We see here again drag coefficients for a sphere here, this line here, and also a bunch of other axisymmetric bodies. For instance, a disk here, which has a drag coefficient almost constant of roughly 1. And I would like to point out this line down here for this airship shape, or it's like a drop shape. It's axisymmetric, so it has a pointed tail. And of course, no surprise, the drag coefficient here is significantly lower. And if we look specifically, for instance, here at the Reynolds number of about, let's say, 200,000, we do have a drag coefficient of of 0.05 compared to a drag coefficient of a disk of around 1. Let me quickly do a calculation on the blackboard just to highlight what this really means. So if we have for our little disk a drag coefficient of approximately 0.05, and for our airship-shaped, droplet-shaped object, sorry, this is 1 and this is approximately 0.05. This is what we got out of the diagram. And we know that we can compute the drag force D equals 1/2 rho U squared A times this drag coefficient. So if we assume that this disk has a cross-sectional area of A, in order to get the same drag force, the A of, what do we call this? An airship, An airship is called. Of the airship needs to be approximately 20 times that of an A disk, right? Because we have a ratio of about 20 in the drag coefficient. So in order to get the same drag force, this needs to be about 20 times larger needs to be 20 times larger in the cross section. Or if you do this by the diameter D, and here again, a large diameter D, we see here that this is approximately the square root of 20D, which is roughly 4.5 D. So what does that mean? That means, and this is why I drew it in that size, if our star of our airship-shaped object is roughly 4.5 times larger than this, and if I did it correctly on the blackboard, this is roughly the size ratio. It's roughly factor 4.5. Well, probably it's even a bit less, a bit smaller here. Just look at these two objects. These two objects have the same drag. So I think this is quite, well, counterintuitive, at least to me, that these two objects would have exactly the same drag. So this is something like that comes out of these diagrams and something to remember here. Okay, so let's move on and let's look at specifically at applications of what we have learned so far. Sports ball aerodynamics. I'm sure all of you have seen at one point plays like these. This is I think from a World Cup final, Brazil against France many years ago. I just want you to see how the ball is hit and how this ball makes a curve to the left. You can see it better in the next view. Now the ball is spinning and is curved to the left, massively curved to the left. And of course, this phenomenon is known, and many people, and many people are talking about this, the F in soccer play, and we can try to understand this. But the first example I want to make is a sport that maybe not all of you are so familiar with, but it's cricket. And it's a very nice application of exactly this story. It's not exactly a spinning ball, but it has also to do with creating a curved ball. So what do cricket balls look like? Cricket balls look like the one shown here on the right. It's a ball about that size, and it has I lost the word. It has a suture going all around the circumference of this ball. The suture stands out a little bit. This is schematically shown here on the left. And what the cricket players are trying to do, the guy who throws the ball, he's trying to throw it in a way that the suture line is at an angle of 20 degrees to the direction of flight of the ball. So he's throwing this ball without any spin, just straight, such that the suture line is tilted. Why does he do that? Well, think back of what I told you about the golf balls, the dimples, they may trip the boundary layer. That's exactly what is happening here. Because in this configuration, the size of the ball, the speed with which the ball is thrown, we are at the Reynolds number, which is below this critical Reynolds number of 300,000 for the drag crisis. So on the upper side of the ball, where there's no suture line, no obstacle, we have a perfectly laminar boundary layer, and we have flow separation here. And we get a flow velocity or a flow velocity resulting in pressure denoted here on the bottom right by this red dot. So it's a reduced pressure because the flow is accelerated, but it's reduced by only a little bit. On the bottom side of the ball, the flow is tripped. The laminar boundary layer is tripped by the suture line. It's tripped in a way that the boundary layer becomes turbulent. So even though the Reynolds number is too low for natural transition, we obtain a forced transition due to the suture line. The boundary layer is turbulent and remains attached for much longer, and the separation point is back here. So we're on the solid black line, and here at the 90 degree point, we're in this configuration. We have a much lower pressure. The flow is much faster. And so the resulting force, this is now a lift force and not a drag force, results a lift force pulling the ball in downward direction, or if we look in the direction of flight, it's pulling it to the left. So we get a curved ball to the left, just by using transition from laminar to turbulent boundary layer, which modifies the wake. The wake is tilted in the upward direction. So this is what creates what they call the swing of a cricket ball. It's quite sophisticated fluid dynamics that does that. What about soccer and tennis balls? So like in the movie you have seen before. Well, people usually think, those who had some fluid mechanics but didn't hear this lecture, they usually think about the Magnus effect. We quickly talked about the Magnus effect in the context of potential flow. That's what you see on the bottom of this slide. You remember that we have a potential flow solution for a cylinder, and we can add circulation to it. We add an ideal vortex to it, which then accelerates the flow on the top and decelerates the flow on the bottom. And through Bernoulli, an accelerated flow will have a lower pressure than the decelerated flow down here. So we have a net force pointing up. This is known as the Magnus effect. Now, what we see in a soccer ball with spin or in tennis ball with spin, like top spin or slice, is not exactly the Magnus effect. It's related, but it's not. It's more complicated. Let's look at this situation here on the left, top left. We are at the Reynolds number, which is below the critical Reynolds number. So without spin, without any spin, both boundary layers on the upper side of the ball and on the lower side of the ball would be laminar. They would both separate at the same point at, what was it, 82 degrees, right, and create a big wave. Now with the spin, as it is indicated here, the flow is accelerated here, which gives it, which makes the relative velocity between the ball and the flow lower. So the flow will certainly remain laminar, whereas at the bottom side, the wall is opposing the velocity of the wall. The ball surface is opposing the velocity of the fluid. So the relative velocity on the wall is higher. So locally, this boundary layer sees a higher Reynolds number, a higher velocity. So locally, this boundary layer becomes turbulent. It becomes turbulent and remains attached longer. So we get an asymmetric flow separation. And again, same story as for the cricket ball, just for different reasons, but the end story is the same. We have a turbulent boundary layer at the bottom, a laminar boundary layer at the top. We get a curved ball again, downward or to the left of the direction of flight. The cool thing about this is that this effect can change if we increase the Reynolds number. If we go in the first place well beyond the critical Reynolds number, then both boundary layers will be turbulent. And we cannot play the game of different separation points anymore. Both are turbulent, both remain attached. And now, very similar to the Magnus effect, it is mainly the higher velocity here, which shifts the separation point a bit to the right and creates a bit of a higher velocity, a bit of a higher velocity and a bit of a lower pressure here, such that the ball goes in the opposite. But just by hitting the ball a bit stronger, going into high Reynolds number range, or a bit less, going to low Reynolds number range, we can decide which direction it will curve. Quite cool and quite sophisticated how this works. So these are a few examples for sports ball aerodynamics. Let me finish today's lecture with a little bit of airfoil theory. Maybe before we start, just a few words on that. You might think that as biomedical engineer, you don't really need to look at airfoil theory because you're not creating any airplanes inside the human body. But just think of the situation that you're designing an implant, be it a pump for blood flow, or let's say any kind of pump. You will always have structures which are airfoil-like, like a vein in a pump. Or if you're designing heart valves, mechanical heart valves with these flaps, they also act like airfoils in a fluid stream. So airfoil theory is also relevant for biomedical engineering. But for next 10, 20 minutes, we're just going to forget about heart valves and blood pumps. We're just going to look at the classical airfoil. And just first, a few definitions. There's a few names and terms that are being used that are well defined for probably well over 100 years. In an airfoil, we call the whole length of the airfoil, we call this the chord length. And we talk obviously about the trailing edge, and we talk about the leading edge here. And the connection between the leading edge and the trailing edge is the so-called chord line. And the angle between the chord line and the direction of the oncoming flow, so the direction of the u velocities here, and the chord line, this angle in between is called the angle of attack, or the angle of incidence in other applications. So in German, it's the Anstellwinkel. And this is certainly one of the most important angles if we want to determine the lift and also the drag of an object, or of an airfoil. The second very important characteristic of an airfoil is the so-called camber, the camber line. In German, this is the Wölbung. So a symmetric airfoil has zero camber, keine Wölbung, and an asymmetric airfoil will have a bit of camber. So it's a bit of a bending of the airfoil. And these are the basic variables or geometrical quantities with which you can define airfoils. Yeah, the thickness, and of course there's a bunch of other more complex parameters. But for a basic airfoil theory, this should be sufficient to understand what we're going to do in the flow. Now, in order to understand what the flow looks like around such an airfoil, there's a beautiful theory based on the potential flow theory. And this theory becomes a bit complicated mathematically, and I'm not sure we're going to go through all the details, but at least I want to give you an idea. It is based on the complex potential. I hope you remember in the second lecture on potential flow theory, we looked at complex potentials where the x and the y coordinate were represented by the real and imaginary parts of a complex number. So the complex potential usually was called W of Z, and Z is equal to x coordinate plus I, y. Now, the complex potential is an analytic function. We talked about analytic functions, that they automatically satisfy the Laplace equations for the potential and for the stream function. So they're always solutions of potential flow. Now, with analytic functions, you can do many things. And one of the things you can do is you can map them. You can do a coordinate transform. And there's a certain family of transforms which are called conformal mappings. And what they do is, well, they change the geometry, change the coordinate system, if you like, and they're conformal in the sense that they maintain the analytic properties of the solution. So if we take such a complex potential W of Z and we do a conformal mapping with it, the solution, the mapped solution, is still a solution of the potential flow theory. Okay, maybe I should show you a picture to clarify that. By the way, this conformal mapping is called the Joukowski transformation, or in the US they usually call it the Joukowski transformation. I'm not sure what is the right pronunciation. I just call it Joukowski transformation. Mathematically, Joukowski transformation looks like the boxed variable. Boxed formula. So what do? You go from a plane which we call the zeta plane, and this would be our normal plane in which we worked before. We called it the z plane. It's a bit unfortunate that they use a different variable, but this is the coordinate system that we usually worked in. And in this zeta plane, you look at the potential flow solution of the flow around the cylinder. Right? We know how to do this. We did this. It's a parallel flow plus the dipole that creates the flow around the cylinder. If we now take this zeta variable, which contains the x coordinate, or here it's called the psi coordinate, and the eta coordinate, and we do this mapping into this new coordinate, which is now called the z plane, then any circle which is mapped with this coordinate mapping, with this conformal mapping, becomes a degenerated circle, or actually just a flat line, which goes from minus 2b to plus 2b, and where b is the radius of this circle. If instead of a circle which is at the center, at the origin of the coordinate system, we shift the origin a little bit to the left. And again, we do a mapping of this circle with the same function. The mapped shape now already looks quite a bit like an airfoil. No? So shifting the circle a bit to the left on the zeta plane creates a blunt leading edge. What happens if we shift the circle a bit upward? So instead of a bit to the left, we shift it a bit upward. Instead of a straight line, we get a line with a bit of camber. Okay? So we can take a cylinder, shift it along the x-axis, and we create a blunt leading edge. The more we tilt it, the more blunt, the bigger the radius becomes on the leading edge. And the more up it goes, the more camber we can generate. And of course, we can combine the two, shift it to the left and shift it a bit up, and we get a cambered airfoil. And so this is a way to parameterize a whole family of airfoils, and this family, surprise, surprise, is called the Yukovsky family of airfoils, Yukovsky airfoil, which you can parameterize quite easily, and you get a large range of airfoils. So now why is this useful, this conformal mapping or this Yukovsky transformation? Well, I told you that we know how to compute the flow around the cylinder, around the circle. We know that. We have done this in the first lecture on potential flow theory. We take a dipole and we add a parallel flow to it. Now, if we take the complex potential of this solution around the cylinder and we do a mapping with the Yukovsky transformation, we obtain the potential and the streamline function, the stream function for the respective airfoil shape. Okay? Here's an example. On the top, you see a cylinder or a circle, if you like, which is shifted a bit to the left and shifted a bit up. So left creates this blunt leading edge, shifting it up creates the camber. The parallel flow actually is not exactly from the left. We tilted it a little bit, which we can do. We know how to tilt, change the direction of parallel flow in a parallel flow solution. And we changed it actually by the angle alpha. Right? In addition, what you probably should also notice, someone added a little bit of circulation to it. Right? We're allowed to do this. This is the Magnus effect. We can just add to the parallel flow, to the dipole, we can also add an ideal vortex to add some circulation. So this is the solution in the top diagram. This is something we have done 3 or 4 weeks ago. If you take this complex potential, and the complex potential, you can just write it down. You have the tables, you just write it down. It's one line. if you take this complex potential and do the Joukowsky transformation, which I admit is a bit of work on pen and paper, but it's technically straightforward to do, you will get the potential, the complex potential for this airfoil you see on the bottom. And if you take the real part, you immediately have the potential. And if you take the imaginary part, you automatically have the stream function, and you can directly plot streamlines for this complex flow solution. So I find this really fascinating that at least for this family of Joukowsky airfoils, you can very, very quickly and quite accurately, of course with limitations of potential flow theory, predict the streamlines around airfoils, at least the airfoils from the Joukowsky family. Now, there's one thing that some of you might wonder, I have not really told you yet. What about this circulation we're adding? Well, let me maybe go to the blackboard and let's look at this again a bit more carefully so we can understand this. Wipe out that part. So we start off with potential flow around a cylinder, right? And we make sure that we have shifted the cylinder a bit to the left and a bit up, such that we obtain at the end the airfoil shape that we would like to see. And we add an oncoming parallel flow around it, and we obtain streamlines. What we also do, don't have to, but we can do, we can also add a bit of circulation. Sorry, this color thing I used them. So we add a bit of circulation gamma. And this will lead to streamlines, which probably will look something like that. Here we have the angle of attack alpha. And then, let's say here, A, we have the parallel flow. U, angle of attack alpha. B, we add the dipole. This defines, wherever we place it, defines our camber, and it defines the shape of our leading edge. And C, we add an ideal vortex. Which adds circulation gamma. Got A, B, and C that we're doing. And the second thing then is we do the Joukowsky transformation. And we obtain our airfoil with the desired camber bit of camber. We have our angle of attack. And here we have our angle alpha for the angle of attack. And this now, what we can do at the end, let's call this 3, we can now compute the lift. What is the lift? What is the lift of this airfoil? Well, we know from potential flow theory that as soon as we know the potential solution, if it is a potential flow solution, the lift is just simply given by rho u gamma. This is the lift of a potential flow around an object. So whatever gamma we have used here is also the gamma that we have here, because the conformal mapping, whatever gamma is here is also here. That's the property of the conformal mapping, just as the velocity u here remains the same as the velocity u here. Okay, so technically this sounds like an easy story. We know what gamma is, so we just multiply it by rho u and we have to lift. Now the question is, what is the right gamma? What is the gamma that we should use to obtain the right flow? Because just from this flow, well, I probably could double the gamma. Streamlines would look different. I would also obtain a potential flow solution, but the lift would be doubled. So who tells me what the correct gamma is? Because it's important to pick the right gamma, otherwise we have the wrong lift. And this is thing that was not clear for quite some time. And it was a person called Kutta who came up with an idea, which, as far as I know, is not rigorously derived, but it's quite plausible. So what was Kutta's idea? Well, let's say we have a solution which looks like that. And note that we have one streamline, as in any potential flow solution, which is exactly coincident with the surface of our object. And we do have actually here a stagnation point at the leading edge, right? And we do have a stagnation point here at the trailing edge. And that's not obvious that the stagnation point is here. What happens if we took here twice the circulation? Go and look it up in your slides. If we increase the circulation here, the two stagnation points here would move together, right? You have more circulation here, will move together. If you do the mapping, well, probably that one would also be moving which direction? Well, probably this direction, but certainly this stagnation point would not be at the trailing edge anymore, would be maybe somewhere around here. If this was the stagnation point, what would this mean for the flow? It would mean that the flow here at the trailing edge, which is the pointed edge, would have to go at the non-zero velocity around the corner. Because this sharp edge, we have locally at this sharp corner an acceleration going toward infinity. which of course is nonsense and will never happen in reality. This is why the Kutta condition, that's what it's called, the Kutta condition says, Kutta condition says, please select the circulation here such that the stagnation point is exactly at the trailing edge. This is how you determine the circulation, the right circulation, which then leads to the lift force, the correct lift force. So this is the last trick you need to know. And with that, you can compute streamlines, correct streamlines, and lift around an airfoil. Not any airfoil, the airfoils of the Joukowsky family. Yeah, that's essentially what is summarized here. How much circulation is there around an airfoil? Kutta condition, the circulation will have the strength to hold the stagnation point exactly at the trailing edge of the airfoil. That's the Kutta condition. Okay, so with that, we have enough information to compute drag. There's a lot of theory on that. You can play a lot of games, do a lot of analytical work, pen and paper work on these Joukowsky airfoils. And you will actually find that the lift coefficient, now we're going back to this coefficient thing, that this lift coefficient for an airfoil, CL, is actually, to first order, proportional to the angle of attack. So you increase the angle of attack of an airfoil, you will linearly increase the lift coefficient. The drag coefficient actually can be shown to increase quadratically with the angle of attack. Of course, potential flow theory doesn't do that. You need another kind of theory. But let's now just stick with the lift coefficient. What about this beta down here? Well, beta is actually a parameter. Let me go back here. Actually, it doesn't say it here. Beta is actually a parameter defining the camber. So high beta means a lot of camber, Wölbung, and beta 0 means a symmetric profile, symmetric airfoil without any camber. So having a beta, non-zero beta, can be shown to shift the lift coefficient upward, or upward. You can see that here. These are the same airfoils from the Joukowsky family, same, except that this one here at the bottom has 0 camber and the two on top have increasing camber. The 0 camber airfoil goes through the origin, and the higher the camber is, the more the lift coefficient is shifted upward. It also makes sense here symmetrically that this goes, that the symmetric profile goes to the origin, because at 0 angle of attack, the upper side and the lower side look exactly the same, so there's no lift resulting from that. Whereas a strongly cambered airfoil creates lift even at 0 angle of attack. Okay. And the flaps here, you can see them in commercial airliners. If you sit above the wing and look out at takeoff and at landing, they will put out the flaps, and it's not so much to increase the size of the wing, it also does that, but in the first place, it increases the camber. They put out the flaps, they put out the flaps to increase the camber to locally increase lift. It will also increase drag, but at takeoff and landing, you mainly want to maximize lift. Okay, this one thing. Now I want to point out the upper end of these lift curves, lift coefficient curves. You see that they all have a certain end at the top and then they fall down. Now what this is flow separation. This is actually a situation where the angle of attack increases so much that we have a relatively early separation of the boundary layer, the upper boundary layer, from the wall, creating a big wake, creating a lot of drag. Drag dramatically increases. At the same time, this whole beautiful lift concept with potential flow theory and circulation completely collapses, meaning that at this point, at the stall point, the lift coefficient breaks down and drag dramatically increases. And what happens to the airplane? Essentially, it falls out of the air, or, I mean, engineers have learned a long time ago what to do about that. I mean, they usually, if it's well designed, they will pick up speed again and will recover. But in the first moment, they will lose all their lift and will increase drag, which means they fall. So that's the stall condition. So many people are confusing stall with turbulence. Stall is not a phenomenon of turbulence. Stall is a phenomenon of flow separation. And we know separated flow usually has turbulence associated with it, but that's not the problem in the first place. We even know that having a bit of turbulence in a boundary layer may delay the flow separation. So let me come to my last slide for today, which is somehow summarizing this whole airflow theory a little bit. This is what you usually see when you look at the performance of an airfoil or even the whole performance of an airplane. This is the airfoil polar diagram. It combines the lift and the drag coefficient in one diagram. So the diagrams before, like that one, has the lift coefficient plotted against the angle of attack, or that one has the lift and the drag coefficient plotted against an angle of attack. So what is done in the polar diagram, you take one angle of attack, you pick the drag coefficient, and you pick the lift coefficient, and then you plot it here. For this drag coefficient, we have this lift coefficient at this angle of attack. And that's, you go through all angles of attack, and we see here at the maximum angle of attack about 15 degrees, the typical angle of attack for a stall, you get the maximum lift. And if you increase the angle of attack even a bit more, you get the stall condition. If you reduce the angle of attack to 0 angle of attack, you will still have lift. If it's a cambered airfoil, you certainly still have drag because you have friction drag and pressure drag. And there's a condition here at alpha 0, which is typically a negative angle of attack, which you have 0 lift. 0 lift doesn't sound like anything sensible, but that's actually what aerobatics airplanes are doing. If you want to do a nosedive, straight down, your direction of flight is straight down. If you had any lift, you would go like that, you would recover. So if you want to, in an aerobatics program, straight down, or, well, of course, for that matter, also straight up, you want to fly in this condition at the alpha naught at the slightly negative angle of attack in order to create 0 lift, and so on. And there's this optimal point here where the ratio between lift over drag is optimal. So you have the most lift per drag, and this point is found by putting a tangent from the origin onto this curve. And this is actually optimal flight condition. So cruise speed for commercial airliners usually is related to this point, or for non-powered airplanes like gliders, you will have this lift over drag optimal condition if you want to get as far as possible with as little drag. So this all a little bit summarizes what we can say here about this airfoil theory. Of course, there's a lot more that we could talk about, but I think we should stop here. And I would well like to hand over to Kai at this point. We'll meet next week again for electron compressible flow, which is quite a bit different from what we have talked about so far. So more or less what we have done today closes the major part of this course. Next week, compressible flow, completely different concepts, different stories, but equally important. So with that, thanks a lot for attending, and I'll see you again next week. And now, Kai, please take over. Thank you.